All right, good afternoon, evening, or morning, ladies and gentlemen. Welcome back to yet another episode of CS341 Algorithms, the final episode in this case. And you'll have to forgive me if I end up sort of slurring or stuttering slightly because I was eating a scallion pancake and I bit the ever-loving crap out of my tongue, so talking is hard. But we'll get through it. Let me take a little sip of my coffee here. Today we're going to be talking about, we're going to wrap up NP completeness with one final poly transformation. And then we're going to introduce a complexity class called NP hard, and finally the complexity class called Undecidable. Okay, so if you sort of remember what we did last time, we started with this satisfiability problem, and we found a polytime transformation from satisfiability to a restricted form of the problem called 3-sat, where all of the Boolean formulae's clauses have exactly 3 literals. We ended up proving that every problem in NP can be transformed to sat, which can be transformed to 3-sat. Thus, every problem in NP can be transformed to 3-sat. And we also proved that 3-sat was in NP. Therefore, 3-sat is NP complete. Now, we're going to cover one more transformation so we can extend this diagram. And this transformation is going to be from 3-sat to another problem we've mentioned before, the Clique problem. So we're going to prove that 3-sat is polytime transformable to Clique. So let's see this transformation. And again, transformations require a huge amount of creativity when there isn't an obvious direct connection between the two problems that you're transforming, so you might have to try a bunch of different things to find a transformation that actually works. You might have to think very carefully about what ultimately might end up being a very deep connection between two problems to find the most natural transformation, or even any transformation that works. So I'm going to sort of present a transformation here. At first, I'll just show you the transformation, and then as I go through the correctness arguments, hopefully it'll start to make a lot of sense why the transformation actually works, why it's a correct polytime transformation, why there is this connection between the 3-sat problem and the Clique problem. Okay, so let I be an instance of 3-sat. So what is 3-sat? Of course, it's a Boolean formula that consists of a bunch of variables that appear as literals, which are either the positive variable xi or the negation of that variable, not xi, and those literals appear in clauses. Clauses are disjunctions, they're logical ORs of 3 literals, and there are m of these clauses, and the clauses themselves are anded together. So in order to satisfy the whole formula, you have to satisfy every clause, which is possible if and only if you can satisfy some literal from each clause simultaneously. You have to be able to satisfy at least one literal from every clause simultaneously by a single assignment of true or false to all of these variables. So there should be a way to assign x1 through xn individually to true or false, so that that total assignment of all those n variables renders the entire formula true or satisfied. Okay, and the 3-sat problem is the question for such a formula: is there a satisfying assignment, yes or no, of all these n variables? Okay, so for example, here is a 3-sat formula with 5 variables, x1 to x5, and 4 clauses. So we have the first clause is x1 or not x2 or not x3. So if x1 is true, this clause is satisfied. If x2 is false, this clause is satisfied. If x3 is false, this clause is satisfied. And here's another clause with not x1, x2, x3. If any of these literals, not x1 or x2 or x3, if any of those 3 literals are satisfied, then the whole clause is satisfied, and we have the conjunction of all of these clauses. So to make the whole formula true, we have to satisfy every clause, which means satisfying some literal from each clause. Okay, what we're going to do is we're going to reduce this formula problem to a graph problem, to the Clique problem specifically. So given an instance I of 3-sat, not this example instance, of course, but an arbitrary instance, we're going to construct a transformed instance that consists of a graph and the size of the Clique that we're looking for. Okay, so we're going to reduce. You'll see at the end. We're going to reduce an instance of 3sat with m clauses to a graph where we're looking for an m clique. Okay? So let's see how we do this actual graph construction. Well, we're going to construct for every literal in the input formula. So how many literals are there? There are m clauses. There are 3 literals per clause. So there are 3m of those literals across all the clauses. And we're going to construct a node for each literal. So we're going to construct 3m nodes. And I'm going to label the nodes or vertices v sub l super c, VLC. So what's VLC? Well, v is the node corresponding to literal number L in clause number 1. So for example, for this first clause and first literal, we would create a node v11. For this second literal in the first clause, we would create v21, v sub 2 super 1. For this third literal in the second clause, we would go v sub 3 super 2, v2 3. Okay, because sorry, v sub 3, so v3 super 2, v3 2. Okay, so v sub literal number, super clause number, second clause, third literal. Okay, so what does this look like? We take all of our literals. How many literals do we have? In this case, in our example that I'm going to sort of draw, pictures for to make this proof, an explanation and subsequent proof a little bit easier to understand, we have m clauses, 4 clauses, 3 literals each, so we have 12 literals in total. So for the first clause here, just for the sake of visualization, I'm going to draw the graph with all the literals in columns and the clauses in rows. The vertices corresponding to clauses in rows, the vertices corresponding to like literal number in columns. So this is first literal in the first clause, second literal in the first clause, third literal in the first clause. You can see x1, not x2, not x3. And you can imagine that the way that we're going to store this data in the graph, we want it to be very efficient for the sake of our algorithm. It is a convenient way to express our data, if we can sort of make it easy to access the corresponding literal for a particular node. So you can imagine that behind the scenes, these nodes are actually labeled 1 up to 3m, right? And they're stored in an array. And I can have an array containing information about the literals that are associated with those nodes, right? So I can in constant time, given a node name, I can look up the literal information for that node in constant time. That's how I would really implement something like this. Okay, so we have our first clause. Let's add our second clause. So our nodes will be not x1, x2, x3. So this is v super 2, so the second clause, and sub 1, 2, 3 for the 3 literals. And we'll add these nodes for the other 2 clauses, right? So in general, we'll have 3m nodes, 3 nodes per clause, m clauses. Now, we're sort of, I've said, if we were to implement this, we would really store this literal information in some place where it's very convenient for us to get to the literal the information about the literal corresponding to this node, given the name of this node, right? But I haven't actually explicitly encoded anything, about whether these x1s or x2s or x3s, these literals are positive or negative. I haven't encoded that in the number of nodes or whether I created a node or not. So sort of the information about the relationship between the literals in these different, corresponding to these different nodes is going to have to be encoded in the edges of the graph. So what are the edges of our graph going to be? We're going to try to somehow encode logical consistency or contradiction between the literals associated with these nodes. So for example, if I were to draw an edge from v11 to v12 here, that would be an edge between 2 nodes where the node's literals are positive x1 and negative x1. So this node would represent x1 being set to true, and this node would represent x1 being set to false in order for these literals to be satisfied. And I don't want to draw an edge between those two, because in order to satisfy the literals for both of these nodes, I would need to contradict myself. I would need to set x1 to true, and I would also need to set x1 to false. I would have a contradictory truth assignment in order to satisfy both of the nodes connected by such an edge. So I don't want to add such edges to the graph. I also somehow want to encode in the graph that I'm satisfying the So edges in the graph are going to represent simultaneously satisfying the literals associated with two nodes. So for example, I could draw an edge between v11 and v22, and I can simultaneously satisfy x1 and x2, right? I just set both of them to true, and I could simultaneously satisfy those two. So I'd like to add edges between pairs of nodes where I can simultaneously satisfy the literals associated with both of those nodes. But I actually don't want to draw edges between a pair of nodes that are in the same clause, because intuitively, I don't care about simultaneously satisfying multiple literals in the same clause. I want to satisfy literals in different clauses. I want to satisfy all the clauses. All I care is that for each clause, there's something I can satisfy, some literal I can satisfy, and I can satisfy all of those literals together, one literal in each of the M clauses, all at the same time. Okay, so I'd like to have sort of, one node in each clause that I select, and to be able to satisfy all of the literals associated with those, M clause, with those M nodes, so one literal from each clause. I'd like to be able to satisfy all those literals simultaneously. So I don't want edges between nodes in the same clause, because they would represent satisfying multiple literals in the same clause. That doesn't help me. I want to satisfy literals in different clauses. So here's how I'm going to define my edges. I'm going to draw edges between all non-contradictory pairs of nodes, meaning I'm not going to draw an edge between xi and not xi, but any other combination of, xi, x1 and x2, or, not x2 and x3, or not x2 and x5, or not x2 and not x5. Those are non-contradictory. I can simultaneously satisfy both of those literals. So I will draw such an edge as long as that pair of nodes represent different clauses. So that pair of nodes should be in different clauses and should be a non-contradictory assignment. I will add all such edges between all pairs of nodes. Okay, so let's do this, for example, in our example here. So let's consider all of the edges that are going to come out from v11. So we want to consider all the nodes in different clauses, so not v12, not v13. Sorry, not v21, not v31. So all the nodes in different clauses that represent non-contradictory truth assignments that aren't not x1. So we're not going to draw an edge to v12. We are going to draw an edge to v22, to v32, right? So we'll draw these edges. Can we draw an edge between v11 and v13? Is it non-contradictory, the assignment of x1 to true and x2 to false? That's non-contradictory, so we'll draw that edge. We can draw an edge from v11 to v23, from v11 to v33. That's fine, we can draw those. We can in fact draw to all of the other edges, to all the other nodes in the graph. Those are all the edges coming from v11, or incident to v11. Well, how about the edges incident to v21? Well, we want to draw edges to every node that's in a different clause that doesn't contain the negation of this literal, that doesn't contain x2. So we can draw edges to this node v12, v32, v13, v23, v33, v14, v23. I just realized my numbers here are wrong. These are all supposed to be v14, v24, v34. That's funny. I didn't notice that before. So we can draw all these other edges. We can do this for every node in the graph. Eventually you end up with this monstrosity that, at this point is sort of hard to understand. We can't really look at this graph and glean any extra understanding from it, but you can understand how I came up with this huge number of edges in the graph. And you can understand what these edges represent. I can simultaneously satisfy the literals associated with two endpoints of an edge without contradicting myself. Now, what would it mean if there's an edge from like v11? Let me back up a couple steps here. If there's an edge from v11 to tons of different nodes here, right? What does that mean? There are edges from v11 to all these different nodes. That means I can simultaneously satisfy v11, x1. My assignment of x1 to true will not contradict any of these assignments. These assignments might contradict each other. For example, x3 contradicts not x3. But my assignment of x1 to true would not contradict setting any of these literals to true. So I'm learning that I can set x1 to true, and I'm allowed to set any of these other nodes literals to true, and they might conflict with each other. Their truth assignments might conflict with each other, but their truth assignments won't conflict with my truth assignment of setting x1 to true. So somehow the existence of edges from v11 to tons of other nodes means setting x1 to true won't conflict with any of those other nodes. Okay, so what does it mean if there's a clique in this graph? It means there's some set of nodes that all point to each other. There's all pairs of edges between those nodes. That means, for example, x1 points to a bunch of other stuff. I can set x1 to true and it won't conflict with any of those other nodes literals in the clique. And for every one of the nodes in that clique, if I set that particular node's literal to true, if I satisfy that node's literal by setting its variable to true or false as appropriate, that assignment won't conflict with satisfying any of the other literals in the clique. So you get this sort of intuition, I hope, that if there's a clique of nodes, then we can actually simultaneously satisfy all of the literals represented by nodes in that clique. So we're going to try to reduce the problem of satisfying all M clauses to the problem of finding an M clique, which will hopefully consist of M different nodes from M different clauses. And the fact that it's a clique will mean we can satisfy all of those nodes' literals, which are all from different clauses, simultaneously. So that's the idea. Let's prove that this is a polynomial transformation. So first, let me show that it's polytime. So I have to pick some reasonable representation of the 3-sat input. So my reasonable representation will be an array of M entries that represent clauses. Each of these clauses is a triple of literals. Each of the literals is a pair containing a vertex name. The vertex name is going to be in sorry, not a vertex name, a variable name. Sorry, this is the 3-sat formula. So the literals will be a variable name, which I'm going to assume are going to be just, v is a number in 1 to n. All the variables are just named 1 to n. And then a negation bit, which specifies whether this literal means like variable x1 or negative variable x1. So this negation bit is just a single bit. And for simplicity, I'm going to assume unit costs for variable names, meaning I'm going to assume that the variable name can be written down in order 1 space complexity, and I can read and write variable names in order 1 time complexity. This is just a simplifying assumption. The results that I'm going to show you here will not change if you don't if you don't assume unit costs. If you work in the bit complexity model instead, and you assume that variable names take log n, bits to write down, the complexity results here will not change meaningfully in the sense that you will still be able to show that this is a polytime transformation. Okay, but assuming unit costs, the size of this input is actually just 3m, because we have m slots for the order 3m, because we have m slots for the array, 3 literals in each. Each literal is a constant number of bits under this unit cost assumption, so it's order 3m bits to write down the input. Okay, so what's the runtime? Well, think about how we would actually construct this graph instance. Let's say we would use an adjacency matrix representation. So we would have to construct an adjacency matrix. How many nodes are there in the graph? There are 3m nodes, and we'd be constructing an adjacency matrix which has, it's of size 3m by 3m. So the whole adjacency matrix is of size 9m squared. That's order m squared size. And if you think about how we're constructing this graph, we go through each clause, through each literal in the clause. So it's like a couple of for loops with total number of iterations 3m. And for each of those, we're going to figure out which edges should we add to the graph. So we'll go for each node in the graph, which is for each literal in the original input, all 3m of them. We're going to go through for each other node in the graph. So we're going to have for loops taking us through all the nodes and then through all the nodes again. And for each pair of nodes, how many pairs are there? There are 9m squared pairs. We're going to check, is this a contradictory assignment between this pair of nodes, and are they in different clauses? Those are constant time checks. So in order to figure out should I add an edge, it's going to take constant time per edge, and in order to add the edge to the adjacency matrix, it's going to take O of 1 time to just write, yes or no, is there an edge in that particular slot of the adjacency matrix. So we create an adjacency matrix of size 9n squared. We set each edge to true or false. We're doing this in constant time per edge, and we're iterating over all of the possible edges, which is 9n squared combinations of vertices, pairs of vertices. So that's all doable in order m squared time. So is order m squared time polynomial in the size of the input? Well, the size of the input's order 3m. If we take the size of the input, we square it, we get order m squared, right? So Well, that's fine. Order m squared is a subset of order m squared. Well, okay, so this is polynomial in size of I, because all we really had to do was square size of I, and we get something that's at least order of what we're looking for. Okay, so the runtime of this transformation is going to be polynomial, sorry, it's going to be polynomial in the size of I. Okay, so we showed the complexity result. Let's show the correctness results. So we're going to do two directions. Okay, we're going to first suppose that I is a yes instance of 3sat, and we're going to show that the transformed instance is a yes instance of mclick. So if there is a satisfying assignment of the original m clause 3sat formula, then in our transformed input, the graph, there is an mclick. Okay, and then we'll prove the opposite, that if there's an mclick in the transformed instance of our input in the graph, then in the original input there was a satisfying assignment of all, covering all m clauses. Okay, so that'll be case 2. So let's do case 1. So I is a yes instance of 3sat. So because it's a yes instance, there exists some satisfying assignment. So for example, in our example here, just for illustration, if we set x1 to true, that'll satisfy the first clause here. If we set x2 to true, that'll satisfy the second clause. If we set x3 to true, that'll satisfy the third clause. If we set x4 to false, well, that won't satisfy anything. But if we set x5 to false, that'll satisfy the last clause. So this is an example of a satisfying assignment. One must exist simply because we've supposed I is a yes instance. So consider such a satisfying assignment. Okay, so that satisfying assignment, it satisfies the whole formula. So it satisfies all the clauses, which means for each clause, it satisfies some literal. We will call that literal for clause CI, we will call that literal SI. It's the satisfied literal SI in CI. Okay, so for example, in our example here, for this satisfying assignment that we considered in our example, x1 was a literal that satisfies clause 1. And x2 was a literal that satisfies clause 2. x3 was a literal that satisfies clause 3. And not x5 was a literal that satisfied clause 4. Okay, the claim now is that if you think about those literals that are satisfied, that we've proved there has to exist a satisfied literal per clause. So if we think about some set of SIs, some set of satisfied literals in all the different clauses, one literal per clause. Think about the nodes that correspond to those satisfied literals. The nodes form an mclick. That's the claim. We're going to show that. So here, for example, in our example, here are the nodes that correspond to those satisfied literals. So here's not x5, here's x3, here's x2, here's x1. And in particular, we're saying this is the x1 in clause 1. This is the x2 in clause 2. This is the x3 in clause 3. Because there's an x3 in clause 2 as well, but it's the x3 in clause 3. That's the one that's satisfied. That's the literal that's satisfied in clause 3, right? And then the not x5 in clause 4 is the thing that satisfies clause 4. So highlight all those nodes, and you'll notice that in our example, those do form a clique, a for clique, an m clique. Okay, but in general, the claim is that the corresponding nodes, the nodes that correspond to those literals that are satisfied in each clause, they end up forming an m-clique. There are m of these because there are m satisfied clauses, and there's a satisfied literal per clause. So there are m of these satisfied literals, and they're each in a different clause, right? Just by construction, we said consider a satisfied literal from each clause. So there are m of them, and they're in different clauses. And none of them represent contradictory truth assignments. How do I know this? Because these are satisfied literals. They are all simultaneously made true, made to be satisfied by the satisfying assignment that exists for this yes instance. So this is a real satisfying assignment that actually satisfied all these literals. So it can't contradict itself. It's a non-contradictory, correct, satisfying assignment. So what that means is none of these literals contradict each other, so there must be edges between all pairs of them, which means they form an m-clique. Okay, so we showed if I is a yes instance of 3sat, if it is satisfiable, there is a satisfying assignment, then our transformed input contains an m-clique. Okay? So now let's prove the other direction. Suppose that f of I, our transformed input, is a yes instance of m-clique. It contains an m-clique. We're going to show that the input that we transformed to get f of I is satisfiable. It's a yes instance of 3-sat. There is a satisfying assignment. So suppose f of I is a yes instance. It contains an m-clique. Okay, so just in our example, we'll draw the m-clique. Now that clique contains edges between all pairs of nodes in the clique, right? Because it's a clique. So what that means is, think about when we transform the input I to produce f of I, right? We only added an edge if it was from one node in one clause to another node in a different clause. So every one of these edges represents a pair of nodes in different clauses. So think about what that means. If we think about v11 here, the fact that it has edges to all of the other nodes in the clique means it cannot be in the same clause as any of the other nodes in the clique. And if you think about the fact that v22, so it's in its own clause separately from all the other nodes in the clique. If you think about v22, that's true for v22 as well. It has an edge to every other node in the clique. So it can't be in the same clause as any other node in the clique. So it has a separate clause that it's in that's different from all of the other nodes in the clique. That's true for every node in the clique. Every node in the clique is actually in its own clause, different from the clauses of all the other nodes in the clique. And there are m nodes in the clique. They're all in their own clauses. So each of these nodes is in a unique clause. There's one node from each of the m clauses. So what if we take all of the corresponding literals in all of those m clauses, the literals that correspond to each of these nodes, and we set them all to be satisfied? So in other words, if we think about like x1 here, we're going to set x1 to true. We're going to set the variable to true because x1 is a positive literal. And for not x5, we're going to set x5 to false because not x5 is a negative literal. So we're going to set the variables that are in these corresponding literals appropriately to true or false to make the literals satisfied. Okay? And well, as we do that, are we going to be building a consistent truth assignment, or will we introduce a contradiction so we can't build a truth assignment out of the assignment where we satisfy all these literals? Well, the clique doesn't contain any edges between contradictory literals. So no edge connects xi and not xi. So for each of these literals represented by nodes in the clique, we can set the whole literal to be true. So not x5 to be true, x3 to be true. We can set each of those to be true, and we know there's no other, negation of that literal in the clique. So when we set not x5 to true, we know there's no x5 in the clique. So we can't introduce a contradiction by setting not x5 to true. So we will have a consistent truth assignment to variables that are involved in the clique that will satisfy every literal in the clique, and in turn satisfy every clause in the formula, and in turn satisfy the formula. Okay, but there's one little minor point I have to make, and that is x1, x2, x3, x5. Not x5. There's no x4 in the clique, right? And it's not necessarily true that every variable will be involved in the clique. So I described here that we'll just assign, truth values to the variables that are involved in the clique based on the literals that are in the clique, satisfying each of the literals that are in the clique. What should we do for the variables that are not in the clique? Well, if a variable's not in the clique, it actually doesn't matter. The formulae are satisfied simply by the values that we assign, the truth values that we assign for the variables that are in the clique. If we satisfy all the literals in the clique by assigning all the variables in the clique appropriately, then the whole formula is already satisfied. And for the remaining variables that are not involved in the clique, I can assign them any way I like, and that's not going to somehow cause the formula to be false now. It was already satisfied by setting all of the literals, by satisfying all the literals in the clique. So all the variables like x4 that are outside the clique, I can set them to anything I like. I can just set them all to false. Okay? That will be a consistent and satisfying truth assignment for the formula. So what we've proved here is, if there's an m-clique in the transformed instance, then I is a yes instance of 3-sat. Okay? So we've proved both directions. We've actually proved here that this is a polytime transformation from 3-sat to clique. Okay. So what have we done here? Well, we've shown that, well, I can transform in polytime 3-sat to clique. And of course, we can transform every problem in NP to sat in polytime. We can transform sat to 3-sat in polytime. We can transform 3-sat to clique in polytime. Okay? So I can transform every problem in NP in polytime to Clique. Does that mean I've shown that Clique is NP complete? Well, almost. I have to show that Clique is actually in NP. But okay, if I were to show, and I won't do it here in the interest of time, but if I were to show that Clique is in NP, then actually I would have shown that Clique is NP complete as well. And in reality, Clique is NP complete. Okay, but we can add another edge actually to that diagram. If you remember last time, we talked about the vertex cover problem and its relationship to the Clique problem. So if you remember the vertex cover problem, the question is there a vertex cover of size k in a graph? What does that mean? Can I pick k or fewer nodes in the graph so that every edge in the graph is incident to some node in the vertex cover? Can I pick k or fewer vertices that together touch all of the edges in the graph? And if you remember, we actually reduced Clique to vertex cover. We showed that if there's we transformed Clique to vertex cover. So we said we can solve the k-Clique problem by finding an n minus k vertex cover. Okay, so this polynomial transformation was proved last class, and if we showed additionally that vertex cover was in NP, this would imply that vertex cover is actually NP complete. And in fact, it is true. Vertex cover is NP complete. Okay, so normally in this course, I would actually prove several more reductions with like the 2 remaining lectures. I'm not going to do them. I'm not going to do that. We don't have two remaining lectures. We don't have any remaining lectures. So I'm in fact not going to tell you at all how these reductions work or these transformations work. But I'll just tell you that they exist, that we would normally do them. By the way, a few times I sort of trip over myself and I say reductions when I mean to say transformations. I want to make the difference between a transformation and a reduction very clear for you. A transformation is a function that transforms the input of one problem to the input of another problem. Okay? That's a transformation. A reduction actually solves one problem by using a solution to another problem as a black box. So a transformation is only about transforming the input, subject to the properties that we have to prove, that 3-part proof. That's a transformation. It's about transforming inputs. And a reduction says I can actually solve one problem using a solution to the other problem. And the existence of a polytime transformation implies the existence of a polytime reduction. Okay? And vice versa. Okay, so hopefully that clarifies that. So let's fill in some other edges in this transformation graph, which, by the way, implies a reduction graph. So edges here represent transformations. Transformations, the existence of a polytime transformation implies the reduction, so these edges could just as well represent the existence of polytime reductions. Okay, so normally we would prove that vertex cover reduces or transforms to subset sum, and we would prove that subset sum is transformable in polytime to 0,1 knapsack. Okay, so we would also show that vertex cover is transformable in polytime to Hamiltonian cycle. Well, actually, typically I don't actually end up proving this edge. Sometimes we post kind of a note about this, just showing it, because it's sort of too complicated to go through in class, but it's not too bad if you go through on paper. We won't bother with that this year. And then Hamiltonian cycle can be transformed to the TSP, the traveling salesperson decision problem. So if you remember the traveling salesperson decision problem, it says, tell me, is there a Hamiltonian cycle of weight at most t? Right? So reducing Hamiltonian cycle or transforming Hamiltonian cycle to TSP decision is not too hard. Now, all of these problems turn out to be NP complete, and in fact there are hundreds more known NP complete problems and more being discovered all the time. So there are lots and lots and lots of NP complete problems. It's an enormous class, and it's quite interesting because what that sort of suggests is all of these problems are equivalently expressive in some sense. I can solve all of them by reducing them all to each other. So I can reduce 0,1 knapsack to SAT. I can reduce Hamiltonian cycle to subset sum. You can do the fact that all of these are NP complete means that actually you can reduce all of these to all of each other. Like every pair of these can be reduced to each other. So they're all extremely expressive problems, and it's quite an interesting equivalence class. Now, these two reductions here from subset sum, or transformations from subset sum to 0 on knapsack, and from Hamiltonian cycle to traveling salesperson to decision, I've actually included slides at the end of this slide deck because I'm leaving these as home exercises for you. These would be probably the two easiest reductions or transformations that we do in the course. I say both reduction and transformation here, both because it's a force of habit to say reduction, and also because I actually can't remember whether I'm asking you to do a transformation or a reduction. But whichever it is, there are home exercises at the end where it's sort of, you can view it as a guided exercise. So I'll sort of set up the problem and say, here's what you want to do, and then there's a slide that has a sketch of the solution, and there's like a gray box covering the solution, so you have to open it in PowerPoint and delete that gray box to see the sketch of the solution to figure out if you got it right. So there's some sort of exercises you can do at the end if you're interested. Okay, so that's wrapping up NP completeness. The two things that are left that I want to talk about in this lecture are NP hardness, which will be a very quick discussion, and then undecidability, which will be slightly longer, but nowhere near as long as our finishing of NP completeness. Okay, so what is this NP hardness? Well, we've talked so far about a few complexity classes, P, NP, NP complete. Here's another complexity class called NP hard. What does it mean to be a member of NP hard? Well, NP hard problems intuitively are at least as difficult as NP complete. You can reduce every NP complete problem to an NP hard problem. And of course, that also means you can reduce all NP problems to an NP hard problem. Okay, so if you have an NP hard problem, you can reduce every problem in NP, every problem in NP complete. They can be reduced or transformed to any NP hard problem. So intuitively, if you solve the NP hard problem, you've solved all the NP complete problems, all the NP problems. Excuse me. But intuitively, it's at least as hard as NP, because NP complete has a very strong restriction that you can only be NP complete if you are a decision problem. And NP hard allows you to be any type of problem, not just a decision problem. So if you can reduce an NP complete problem to some problem pi, then pi is NP hard, whether it's a decision problem or not. If it's a decision problem, it's also NP, and it's in NP, it's also NP complete. But either way, it's an NP hard problem. Okay, so here's a formal description. A problem pi is NP hard if there exists some NP complete problem that can be reduced in poly time to pi. So if I can reduce an NP problem, an NP complete problem in poly time to pi, pi is NP hard. Notice, I don't need to show that pi is in NP. I don't need to show that pi is in NPC. I don't need to show that pi is a decision problem. Just if an NP complete problem can be reduced to pi, pi is NP hard. Okay, so that means immediately that all NP complete problems are NP hard, because I can reduce an NP complete problem to another NP complete problem. So if pi is an NP complete problem, you can reduce all the other NP complete problems to pi, so pi is NP hard. Okay? So NP complete is a subset of NP hard. In fact, it's a strict subset, because there are NP hard problems that are not in NP complete. So typical examples of such problems that are NP hard but not NP complete are optimization problems corresponding to NP complete decision problems. So think about the optimization variants of other problems that we've thought of that have decision variants. So for example, we talk about TSP decision and TSP optimization. So optimization wants you to return an actual optimal Hamiltonian cycle, not just a yes or no, is there a Hamiltonian cycle of weight at most t, right? So this is the decision flavor, this is an optimization flavor. We showed earlier on in lecture 19 that you could reduce TSP decision to TSP optimization. This is actually a reduction. This is a Turing polytime reduction. We showed the existence of such a reduction, which means that TSP optimization is NP hard because TSP decision is NP complete. Okay. Similarly, TSP optimal value, we showed that we can reduce TSP decision to TSP optimal value, and so TSP decision is NP complete. So TSP optimal value is NP hard, and we know that TSP optimal value, it's not a decision problem. TSP optimization is not a decision problem. So these guys are not in NP. They're not NP complete, but they're NP hard. Okay, so NP hard is a strict superset of NP complete. This is where we talk about the hardness of non-decision problems relative to other NP complete problems. Okay, so that's what NP hard is. That's all I'm going to say about it. Now we're going to move on to the final topic in the course, which is undecidability. This is a complexity class that consists of problems that are not just difficult to solve in some time, they're actually impossible to solve in finite time. Okay, so let's try to understand what undecidability is, what the undecidable class of problems are, what the decidable class of problems are. So first of all, decidability or undecidability, it only talks about decision problems, right, as the decidable, undecidable name might suggest. So let me define what it means for an algorithm to solve a problem. Okay, what do you mean for an algorithm A to solve a decision problem? Let's be very precise. This is a really technical definition, even though it looks super simple. So make sure you understand this definition very carefully. So in order for an algorithm A to solve a decision problem, the following must be true. Given any input I, no matter what that arbitrary input I is, this single algorithm A, run on input I, must have finite runtime and return the correct answer. That's what it means to solve the problem. It means a single algorithm A that solves the problem should work for any input, so for all possible inputs. This single algorithm A should work for all possible inputs. For every input, it should run in finite time, and it should return the correct answer. Okay, so what is it? Why am I defining what it means for an algorithm to solve a decision problem? Well, if it's possible to design an algorithm A that solves a decision problem pi, then we say pi is decidable. Okay, so A is an algorithm that solves the problem. Pi is the problem. We say pi is decidable if it's possible. Maybe we don't know an algorithm right now. Maybe somebody won't come up with an algorithm that actually solves the problem for 1,000 years. When I say, or maybe nobody will ever be able to come up, no matter how smart they are, no matter how much time passes, maybe nobody will ever be able to come up with an algorithm that can solve this problem. Okay, that's what we're talking about. When we talk about this problem being decidable or not, we're saying, is it fundamentally possible to design an algorithm to solve the problem? If it is fundamentally possible, irrespective of whether we know an algorithm to solve the problem, then the problem is decidable. Okay? So if we ask you to show that a problem is decidable, you must show here is an algorithm that solves the problem. That will be a proof that it's possible to design such an algorithm. It will be an explicit proof by construction. You will show me an algorithm, and by showing me an algorithm that solves the problem, you will prove, by showing me the algorithm, that it's possible to design such an algorithm. Then we'll say that pi is decidable. Okay? If I ask you to prove that pi is not decidable, you must show that it's impossible to design such an algorithm that solves the problem. Okay? So let's get into this formally a little bit. So formally, pi is decidable if and only if there exists some hypothetical algorithm A, right? It exists, we don't necessarily know it, okay? It's decidable if and only if there exists an algorithm A such that for every possible input I, A of I returns the correct answer in finite time. So there must exist a single algorithm that solves every input in finite time. Now, what does it mean to be undecidable? It's the same as decidability, except if it's not possible to design an algorithm that solves the decision problem, then we say pi is undecidable. Formally, pi is undecidable if and only if there cannot exist an algorithm A that will solve the problem for every instance, returning the correct answer in finite time. Okay, it's undecidable if and only if there cannot exist such an algorithm. So this is still sort of something that's hard to prove, because you're talking about cannot exist such an algorithm. What do you mean cannot exist such an algorithm? Well, let's propagate. Oh, sorry, this shouldn't say cannot not. This should just say cannot. Okay, I'll fix that. Sorry about that. Erroneous double negation. This is there cannot exist. Not. I don't mean to say this cannot not exist. That's weird. Okay, if and only if there cannot exist an algorithm A. Okay, well, what do I mean I cannot exist an algorithm A? Well, I can rephrase this as an equivalent logical statement. I can say pi is undecidable if and only if, for every algorithm that does exist, there is an input I such that A of I will either fail to return the correct answer or it'll take infinite time. Okay, that's the negation of there exists an algorithm to do this. The negation of there exists to do an algorithm to do this is every algorithm that does exist cannot do this. Okay, well, what do you mean cannot do this? Cannot, for every instance, return the correct answer in finite time. What's the negation of for every instance we return the correct answer in finite time? The negation is there is an instance where we don't return the correct answer in finite time. Okay, that's the same as saying there exists an input where we fail to give the right answer, we give the wrong answer, or we run for infinite time. Okay, so you can say equivalently, pi is undecidable if and only if for every algorithm A that you could possibly ever write, there's some input I so that A of I will either return the wrong answer or will run forever. Okay, that's how we prove something's undecidable. We would need to prove for every algorithm there exists an input such that that algorithm will return the wrong answer or will run forever. That's how we prove undecidability. Okay, so let's see a problem that's undecidable and prove that it's actually undecidable. So this problem is this super well-known problem, one of the first problems to be proved directly to be undecidable. And you might wonder, how would you prove that every possible algorithm to solve this problem will fail on some input? How could you prove that for every possible algorithm? No matter how smart someone is, no matter how long they spend trying to solve the problem, no one will ever be able to solve this problem. So this is an interesting sort of study if you've never seen an impossibility result like this, such a lower bound before. This might be your first such example in that case. So what's the problem? What's the halting problem? The problem of halting is a decision problem, and you want to answer the question, will some other program that's fed to me as input run forever, or will it halt in finite time? So you could think of this as like you would love to have a halting problem exist because you would love it if a solution to the halting problem existed as a programmer, because what you would do is you would use the solution to the halting problem to debug your programs to find one particular type of bug, right? The halting problem would find infinite loops. So the halting problem, if you solve it, then you could plug your program into the solution to the halting problem, and it would tell you, will your program run forever or will it terminate in finite time? So a solution to the halting problem would let you detect any bugs in a program that are related to running forever. Okay? So you'd be able to prove termination for every program by feeding that program as input to a solution to the halting problem. Okay, let's do this formally. So the input to the halting problem is a computer program A, so like some code, like a string, and an input X for the program A. And the input could be anything, but let's just assume it's written down as a string. It doesn't change anything if we don't assume that, but that'll make it way easier to make this argument. So assume the computer program A is a string, the input X to that program is a string. And what the halting problem is going to ask is the question, if I run A on input X, will A terminate in finite time or will it run forever? I'm going to run A of X. Will it run forever or will it terminate in finite time? The halting problem should answer yes if it'll terminate in finite time, and no if A of X will run forever. Okay, so what does it mean for the halting problem to be decidable? Because we're going to prove it's undecidable. Okay, well, the halting problem will be decidable if and only if there exists an actual algorithm to solve the problem. We'll call that algorithm halt of I. Okay, it takes some input I. So if there exists such an algorithm, halt of I, that solves the problem, then the halting problem is decidable. Okay, that's an if and only if. Okay, well, what do we mean halt of I solves the halting problem? Given any input, what's the input to the halting problem? It's a computer program A and an input to that program X. So we can run A of X. So the input to the halting problem is going to be I equals A comma X. And this solution to the halting problem should correctly answer the question, would a call to A of X halt in finite time? Okay, it should answer that question correctly. And we're saying halt of I is a solution to this problem. And remember what I said about solving a decision problem. To solve a decision problem, you must return the correct answer in finite time. So halt of I is a correct solution to the halting problem. That means halt of I should run in finite time, and it should give the correct answer. Okay, so halt of I, if and only if it's decidable, Okay, if the halting problem is decidable if and only if there exists a correct halt of I. What is it that solves the problem, that solves the halting problem? What do we mean solves the halting problem? Halt of I should run in finite time and correctly output the correct answer. What's the correct answer? It has to correctly answer the question, would a call to A of x halt in finite time? Okay, so I realize this is a lot to wrap your mind around, but please try to think really hard about this and make sure you understand this, because the proof that I'm about to do of undecidability of the halting problem is going to really depend on you understanding this definition. So, and I realize undecidability is a really hard topic for most students. So, if you don't get it right away, it might take a few kind of runs through the material, but do try to make sense of it. Okay, so we're going to show that the halting problem is in fact undecidable. So to obtain a contradiction, let's assume it is decidable. So we're going to suppose that halt program does exist and it correctly solves the halting problem, meaning halt runs in finite time and it gives the correct answer. And the correct answer is the answer to the question, does A of x halt or does it not halt? Okay? So we're supposing halt exists. It's a correct solution to the halting problem. We're going to obtain a contradiction from that. And when we say halt exists and it solves the halting problem, okay, that means halt with input A of x, input I equal to A of x, is going to terminate in finite time. And it's going to answer true if A of x halts and false if A of x doesn't. So it's going to answer this correct response in finite time for any input, right? To solve the problem, you have to be able to solve the problem for all inputs in finite time with the correct answer. So halt solves the halting problem means for every possible input, a comma x, halt in finite time returns the correct answer, true or false, does A of x halt, okay? That's what that means. And as I said, A is just a string. It's like the code, right? And x is just a string. It's the input to be fed to that code as an input. Now, this is where your mind might get blown. Try to stay with me because we're going to do some really weird stuff. A is a string, and its input is also a string. So the halting problem is going to answer the question, is A of x going to halt or not, right? So the solution halt, this algorithm halt that we assumed exists, it's taking this string for A, and it's somehow analyzing or simulating or running the code for A, right? So even though A is a string, it knows how to interpret that string as code and then answer this question correctly. And it knows how to interpret x. It's specified as a string. It knows how to interpret that string as some correct input to A. So it can sort of correctly answer this question, does A of x halt? Now, if we think about the data types here, just the data types to halt, what does halt take as its argument? It takes a string and a string. Okay? And halt has to answer this question correctly in finite time for every input A comma x. For every possible input. Well, the set of possible inputs are just all the strings that we could write down that ultimately describe every program, whether correct or incorrect as a program. You could write down every program. Every string describes some program. It might be a bogus program, but the set of strings describes a set of programs you could write. And we have to answer the correct response, okay, in finite time for every possible program you could input, for every possible input you could provide to that program. Okay, and maybe we count error conditions as halting. Okay, so like segfaulting is halting, or the Python interpreter blowing up is halting, right? But every possible input is valid. Every possible pair of strings, halt has to solve the problem for that input. So okay, we could pass A, which is a string, as an argument to itself. A could run, maybe it would crash, I don't know, but A could run with itself provided as input based solely off of the data types, because the fact that A is a string and X is a string tells us that X is a string input to the algorithm A. A takes a string as input. So we could run the code A of A. Well, that's weird. Why the heck would we want to do that? Well, okay, here's another weird thing we could do that will seem totally unmotivated, but in the end will help us prove that this is undecidable, this halting problem. If we could feed A to itself, then we could use halt of a comma a to ask the question, does a of a halt? Okay, this is really weird. Why the heck would we want to do that? Well, let's try to obtain a contradiction by running halt of a comma a. Okay, here's a weird program called strange. This is a strange algorithm, and I'll explain it to you, but it's super strange. Well, what is this? Strange takes one argument, a, which is a program expressed as a string. The data type is string. And it has some external procedure that it assumes. It assumes the existence of a halt procedure, right? And we've assumed that halt exists, and it's correct, and it solves the halting problem. The first thing it does is it calls halt, a comma a, and it gets an answer in finite time, right? Because we've assumed halt is correct. And halt correctly answers the question, would a of a halt or not? Okay? So, okay, we check if not halt a comma a. Okay, so if not halt is true, then a comma a doesn't halt. A comma a runs forever. Okay, that's what this line is checking. This line is checking if a comma a would run forever. Okay, so if a comma a would run forever, then we return immediately from strange of a. Okay, so strange of a will terminate in finite time. If halt of a comma a runs, if a of a runs forever, then strange of a terminates in finite time. Why is it finite? Because our halt call runs in finite time. Yeah. Okay, but what about the else case? If we don't get into this then case, if not halt is false, if halt is true, well then, in this else case, halt of a comma a is true, so a of a will terminate in finite time. And what does strange of a do in that case? We just get into a loop where I is initially 1, and then if I is not 0, which it is, because we set I equal to 1 to start, then we increment I, right? I will keep incrementing forever. I will never be 0. We will never break out of this loop. So strange of a will run forever if we get into the else case. So when do we get into the else case? If a of a terminates in finite time. So if a of a terminates in finite time, strange of a will run forever. And if a of a runs forever, strange of a will terminate in finite time. What a weird algorithm. So here's an even weirder question. So you might think this is a lot of things to remember at this point. We're thinking about a of a and strange of a, and now we're going to run strange, providing the code for strange as its argument. Now I have to think about a of a, I have to think halt a of a, I have to think about strange of a, I have to think about strange of strange. There's so many things to think about. But no, all you need to think about, all you need to remember is, in strange of a, if a of a runs forever, strange of a will terminate in finite time. And if a of a terminates in finite time, strange of a will run forever. Okay, so if you remember that about strange of a, then what happens when we run strange of strange? There are two cases. Either strange of strange is going to halt, or it's not going to halt, right? One of those two things has to be true. Suppose it halts. Well then, what do we know if strange of strange halts? Looking at the code, it has to return here. So it returns. In what case does it return? Well, it had to see not halt a of a, right? So it sees not halt a of a. So halt a of a is false. Well, what's a? We're not running strange of a, we're running strange of strange. A is strange. So it sees halt strange of strange is false. It sees not halt strange of strange. Well, what does that mean? If not halt strange of strange, then that's telling us that if you run strange on itself, strange of strange will not halt. So we suppose strange of strange halts, and we ended up proving strange of strange does not halt. That's a direct contradiction. So our assumption must be wrong. Okay, well, I mean, strange of strange can't really halt then. Okay, well, let's try this case leads to a contradiction. Let's try the other case. What if strange of strange doesn't halt? Then it has to spin. If it doesn't halt, looking at the code, it has to spin in this while loop forever, right? How would it get into this while loop, where it has to get into this else case? How does it get into this else case? Well, it only gets there if halt a of a is true. And a of a, well, a is strange. So halt strange of strange has to be true, and that means strange running with strange as argument should halt. So we've, in this case, where we suppose that strange of strange does not halt, we prove that strange of strange must halt. That's another direct contradiction. So these are the only two possible cases. Both of these cases lead to contradictions. Is there any assumption that we've made that led to these contradictions? Yeah, the only assumption that we've made in this whole proof is that halt exists. So that assumption must be false, because every possible case leads to a contradiction under that assumption that halt exists. So halt cannot exist. So that means we've proved there cannot be an algorithm that solves this problem for every input, because if there is an algorithm halt that solves this problem for every input, it must solve the problem for strange as an input. And if it solves that problem, then we can actually implement this strange algorithm, and we can feed strange to itself, and we can derive these contradictions. So what does it mean that we've proved that the halting problem is undecidable, that you can't solve the halting problem for all inputs? Does that mean I can never detect an infinite loop in my program? No. The fact that the halting problem is undecidable means I cannot find a single algorithm that will solve the problem in finite time for all possible inputs. That's all it means. It means I can't find a single algorithm that will solve the problem for all inputs. It doesn't mean I can't solve the problem for any input. It just means I can't solve the problem in finite time for all inputs. Okay, but that's sort of a nice thing to realize. That sort of sounds like a niche realization at first, but it's actually practical, because what it means is you can solve undecidable problems as long as you're willing to restrict the set of inputs. Maybe you can't prove it for all inputs, but for a restricted class of inputs, nobody says that you can't detect infinite loops for a restricted set of programs. So undecidability can be a proof that you should give up on solving the general case of all inputs, and to make further progress, you should ask yourself the question, what kind of input restriction will yield a tractable problem that I can actually solve in finite time for all of these restricted inputs, and are also interesting inputs that will, be useful to people? Okay, so when you think about undecidability, I don't want you to think these problems are impossible to solve, so we should never try to solve them at all. I want you to think, if you prove that a problem is undecidable, what you've really proved is that to solve this problem, you should find a suitable input restriction where the problem becomes tractable and is still sufficiently interesting to be worth solving. Okay, so that's the sort of almost all of the material on decidability. The last thing I'm going to do is show you one final undecidable problem. This will be way easier than the previous stuff. I'm going to show you that you don't have to prove that every problem is undecidable from first principles. Just like with NP completeness, the Cook-Levin theorem provided the first NP-complete problem, and by reductions, we managed to show that other problems were NP-complete without proving NP-completeness from first principles. You can do the same thing here. You can take one undecidable problem and reduce other problems to this undecidable problem and prove that those other problems are also undecidable. So let me show you how that works. So consider another undecidable problem called the halt all problem. So this is quite a bit like the halting problem, except where the halting problem takes a program A and an input X to that program. The halt all problem doesn't take the X, it just takes the program A, and it answers the question, will this program A halt for every possible input to that program? So this is sort of more powerful than like the special case of this where we ask, will A halt on only a single input, right? We're asking, will it halt on all of the possible inputs, right? So you can imagine, to implement this correctly, you'd sort of have to explore all of the inputs. This would be even harder to implement in practice than the halting problem. So it shouldn't be surprising that this is going to turn out to be undecidable because the halting problem is undecidable. Okay, so how do we prove that this is undecidable by a reduction? Well, we're going to describe a Turing reduction. This is a reduction, not a transformation, but a reduction. Like the polytime transformations we looked at were about reducing decision problems to other decision problems. Okay, and they were about doing this in polytime. Here we're actually going to show not just that you can transform inputs, but that you can solve the problem using halt all as a subroutine. So that's a reduction, not just a transformation. And here, we don't even care about it being poly-time. It could be an exponential time reduction. Who cares? That's fine, because here we're not trying to prove poly-time results, poly-time computability. We're trying to prove computability, decidability at all. Okay, decidability says, is it even possible in finite time? So we just want to know, is there a finite reduction? Okay, Turing reduction from halting to halt all. Suppose there is such a reduction, what will we have proved? We will have proved that if I have a solution to halt all as a subroutine, then I can solve halting problem. And of course, solving the halting problem, we just showed it's impossible to solve the halting problem if we don't redefine the halting problem to restrict inputs. So if it's impossible to solve halting, but an implementation of halt all, a solution to halt all, would solve halting, that tells us you cannot have a solution to halt all. That will prove that halt all is undecidable. Okay, so let's do this reduction. Okay, so assume we have a solution to halt all called halt all solver. Now, the halt all solver, it takes a program A as input, but it doesn't take the input X, and we're trying to reduce halting, which takes an input, a program A, and an input X to that program. Our input to halting is A comma X. I equals A comma X. Okay, but we can't use that X. We can't pass that X to our halt all solver. It only takes a program A as input. So how are we going to feed our input X to halt all solver? Well, we have to transform our input somehow. And the way we're going to do this is with a technique from functional programming called currying, where we're actually going to construct a new program, BX, that takes no arguments. It has no input. But the code for BX is going to embed directly the code of program A and the actual input hardwired in as an input to program A. So BX is going to have no inputs, and it's going to run, the only thing that BX is going to do is run A of X, where X is hard-coded in the code for B. So BX has no input. So how many inputs are there of B? There's only one, the empty input. And so BX, what happens if we run BX on all of its possible inputs? Well, BX run on all of its possible inputs is just BX run on no input, which is just running A of X. So here's the reduction. Given an instance of halting, which is an A and an X, construct the program BX, which is just going to run A of X where the X is hard-coded. Run halt all solver on BX. That's going to say, will BX halt for all of its possible inputs? Well, what's all of its possible inputs? There's only one, the empty input. And what will it do for that empty input? It will just run A of X. So running B of X for all of its inputs just means running A of X on this, the single input X. So will BX halt for all possible inputs is equivalent to saying, will A of X halt for that particular input? So, halt all solver of BX is going to be true if and only if A of X halts. So, to solve the halting problem, we just have to return the result of halt all solver BX. So, if we have a solution to halt all, we have a solution to halt. That tells us halt all is not solvable. Halt all is undecidable, because if it were decidable, we'd have a solution to the halting problem, which we've shown from first principles is undecidable. Okay, so that's the end of the course matter. I'm going to leave you with a final slide which just kind of gives you a recap of the complexity classes that we've gone through. If you feel pretty comfortable about your knowledge of the complexity classes, you can stop the video now. If you'd like to have a little bit of review, you can think of this last part of the video as not really counting towards the time of the video, because this is sort of like a supplementary review slide here. So let's just recap all the complexity classes that we've seen in the intractability section of the course. And by the way, this slide, if you look at it in PowerPoint, look at the notes on the slide, there are just a few more notes with some extra details if you're curious. Okay, so the first complexity class we looked at was P, problems that are decision problems that are solvable in poly time. Okay, so these are decision problems that can be solved by algorithms, and those algorithms have to have runtime that's polynomial in the input size, polynomial in the number of bits needed to write down the input to that problem, and the input has to be written down in a reasonably efficient representation. Then we had NP, which was non-deterministic polytopes. So these are decision problems for which certificates can be verified in time that's polynomial in the input size. Equivalently, you could think of this as decision problems that can be solved in polytime if you have access to a non-deterministic oracle that returns a yes certificate if one exists. Okay? Then we have NP complete. So these are decision problems. So all of these are decision problems so far, all these classes. They're the decision problems pi that are in NP. They have to. So this only contains a subset of problems that are in NP, such that every other problem in NP can be reduced to pi, and that reduction happens in polytime. And it's generally enough to show that a polytime transformation exists from pi prime to pi for some NP complete problem. And then you also, in order to show pi is an NP complete problem, you have to show a reduction from another NP complete problem pi prime, or a transformation from another NP complete problem pi prime. And you also need to show that pi is in NP. So we've seen proofs at various times about proving something is in NP. Then we talked today about NP hard, which is intuitively problems that are at least as hard as NP complete. You can certainly reduce every NP complete problem, and thus every NP problem, to pi, if pi is an NP hard problem. But notice, we don't need this to be a decision problem. We don't need this to be in NP. So that's what these gaps are, right? It's not a decision problem necessarily, but it could be. And it's not in NP, but it could be. In particular, in order for it to be an NP, it would have to be a decision problem. So the NP complete is a subset of NP hard. And then we have undecidable. This is the set of decision problems that cannot be solved correctly with finite time for every input. So I don't need to go into what that is. You guys have just spent this whole lecture talking about, hearing about that. Decidable problems are a superset of all the problems in P, NP, and NP complete, right? Because these are all decision problems that can be solved in some time, right? So these are all, P, NP, and NPC are all subsets of decidable problems. And the decidable and undecidable are disjoint, right? And NP hard problems, we don't say that they're decidable unless they happen to also be decision problems, right? Because decidable is about decision problems, and NP hard contains some problems that are not decision problems. So you can't say that NP hard is a subset of decidable, but the decision problems in NP hard are decidable. Okay. Now, I can give you a couple examples of each of these just to refresh your memory. So, for example, the decision problem variants, because there are some non-decision problem variants of problems. These have to be decision problems. So any true-false variants of, for example, breadth-first search or Dijkstra's or any of the dynamic programming algorithms where you can prove that they are polytime of the input size. There were some dynamic programming algorithms we saw that are not necessarily polynomial in the input size for all input sizes. So, for example, the knapsack problem, that was not polytime in the input size for all input sizes. So that is not a problem in P. And so that would only be polytime for some subset of the input sizes. I think I have one post on Piazza about that if you're curious. Okay, how about NP? Well, everything in P is in NP. So, and then we have this like vertex cover, clique, sat, subset sum, all these things that we talked about. And then pretty much all of those tend to be NP complete as well, because the set of problems in NP that I talked about in the course happen to be ones that were all NP complete. And then NP hard has all of NP complete, plus you have, for example, TSP optimization, where you have to actually return not just a true-false Hamiltonian cycle of optimal weight. You have to return the cycle itself. For TSP optimal value, you have to return the optimal weight of the optimal Hamiltonian cycle, the weight of the optimal Hamiltonian cycle. Neither of those are decision problems. They are reducible to the decision problem in polytime, but they're not NP complete because they're not decision problems themselves, but they are NP hard, and every NP complete problem, and thus every NP problem, can be reduced to these and to many other NP hard problems, all the other NP hard problems. And then for undecidable, we have halting and halt all, and that's the whole summary, and then we're into sort of home exercises at the end. So I encourage you guys to take a look at those. Thank you all for taking this journey with us through the course. I'm sorry that we had bumpy times, but I really appreciate you guys working with us, in these very trying times. And I hope that we can conclude with a take-home exam that you guys will all do well on, and everyone will be reasonably happy with how this all played out in the end under all the circumstances. So I was super happy to have you guys with me along this adventure. If by the time you see this video the evaluations aren't closed yet and you haven't submitted an evaluation, please consider submitting an evaluation. It's very helpful for those of us who are still up for tenure. And I'll conclude there. We'll be taking questions about the take-home exam on Piazza as if it were an assignment. Please be very careful not to reveal any even partial solutions to your classmates. If you're in doubt, make it a private post. Okay, with that, thank you guys very much, and good luck in all of your future endeavors.